Yeah. Yeah, just if you speak a little loudly and it'll pick you up on here. So. And I'm just gonna stop sharing your screen at the beginning so people can see you and or on Zoom. All right, good morning, everyone. Welcome to week 2, day 7, 8. Just back up to a certain point. Our first speaker today is Dr. Manwar Hassan from School of ECS here. And some of you may know him if you've taken his classes, 360 Systems Programming and 439, the Cyber Infrastructure Security course. So I'll be speaking to us about IoT, cyber physical systems. And without further ado, all yours.
Okay. Thanks, James, for the introduction. As James said, my name is Manwar Hassan. For 39, some of you already know me. So I'm happy to be here. And today I'll be talking about some ideas of protecting actuators in time-critical cyber-physical applications. So let's get started. Let me share my screen. Okay, here you go. Okay, little bit of introduction. So I lead the cyber physical system security research lab, bunch of students working with me, including a couple of undergraduates. So my research mainly in computer systems security domain. I work in the intersection of computer systems, networking, and security, with a more focused on exploring applications of cyber physical applications. So I'll talk about cyber physical systems just in a little bit. So my students and I are looking towards security solutions for time-critical cyber-physical applications, edge computing, Internet of Things. We are looking into resiliency aspects, scheduling, intrusion detection, making security solutions more resource-aware, and research work along this line. And we also started to look into more emerging applications like learning-enabled autonomous systems like self-driving cars, drones, and looking into different learning-enabled workload like machine learning models. How can we make them more resource-aware and using resource-constrained embedded cyber-physical applications, and also at the same time ensure their trustworthiness and tamper-resistance properties. And also, I have one student who is looking into exploring newer networking technologies like software-defined networking technologies to provide better resiliency for cyber-physical networks. And also, recently we started looking into applications of cyber-physical systems, especially looking into cybersecurity for precision agriculture, like if we use the cyber-physical components like drones and smart tractors to provide more precision agricultures. How can we ensure better resource management and also security guarantee? So for today's talk, I will be mainly focused on one key thrust, exploring security for real-time, time-critical or real-time cyber-physical applications. So before I go into the details, so let me give a little bit background on cyber physical systems if you're not familiar with. What is cyber physical system? So as the name says, we have two components, cyber and physical. So in cyber physical systems, cyber components such as the application, control logic, network and communication stacks, and also the underlying embedded hardware board like microcontrollers or electronic control unit in automotive systems, they all coupled with physical components like the sensors, actuators, actual physical plant to make the whole platform, whole system operational. And where we can find applications of cyber physical system, we can imagine all the more use cases in modern our everyday life, including automobiles, avionics, control systems, as well as more emerging applications like remote surveillance, drones, autonomous vehicles, another very classic example of cyber physical applications, and also smart manufacturing, robot-aided healthcare. Those are just a few examples. So we talk about briefly real-time systems and their applications, right? But what about security for real-time cyber physical systems, right? So in the past, in earlier cyber physical applications, those systems use custom hardware, so they are proprietary. They use proprietary operating systems. They use proprietary firmware, and also those earlier systems they were remained isolated, or in other words, they were remained air gap and don't communicate with other competing entities. But with the emergence of modern connected things, uh, newer cyber-physical applications are now getting used of, getting the developers of modern cyber-physical systems now use more and more off-the-shelf hardware and software. They tend to use more open source software, operating systems, APIs, protocols, and also more importantly, they are now become more ubiquitous. They have now more connectivity, and often they communicate over the unreliable medium such as the internet, which means for modern cyber physical applications, now there is a larger attack surface, and those systems, those safety critical systems are now vulnerable to security breaches. There has been some recent attacks on automobiles, police drones, industrial control systems. Those shows those attacks are real. It's not just some academic research. And to protect those safety critical systems, we need a layered defense mechanism. So we need to know from all competing stack, from application, firmware, network, and as long as their whole connectivity resource constraint to take into the account while designing security solutions. And because of some nature of unique properties of cyber physical, time critical cyber physical applications, it's different than general purpose computing systems. So we cannot directly bring any existing security solutions like intrusion detection mechanisms or encryption algorithms and feed into the cyber physical applications because of their inherent properties. And what are those? So let me little bit talk about those ideas, those characteristics of time critical cyber physical applications that make it unique, and also it's at the same time very hard to protect the system, bringing security solutions for safety critical cyber physical applications. So one of the distinguishing characteristics of cyber physical applications is time. So often those time critical applications called real-time systems. So for real-time applications, we need correctness both from the logical side, the functional correctness, and at the same time, we also need temporal correctness, which means certain things needs to be done within certain temporal bound. So there's a misconception about real-time applications. Often people think real-time means fast or just in time, like real-time multimedia. But real-time applications, what we are meaning here in cyber physical, real-time cyber physical applications, which doesn't mean we need to perform fast computation. Instead, what it tells, we need to perform the required functionalities of the applications or tasks within its predefined timing constraint. And often those timing constraints are called deadline. So each real-time applications in the system must meet their deadlines to make sure the system remains operational. So a very classic example of real-time applications is consider the anti-lock braking system of the car. So in anti-lock braking system, when the brake pedal is pressed, the ABS anti-lock braking system module will kick in and prevent the wheel from spinning so that your brake in the car doesn't skid. And it must be done within a very small amount of time. Now, consider a case, say when the brake pedal is pressed, the vehicle ABS module is activated. Now, if there is any delay in between for the process for due to faults or some application bug or even errors, and that spinning process, the spinning prevention process takes some time to activate, then the car could skid and it may hit some another object, right? And to just give you some perspective, this ABS process needs to be performed in a very stringent, within very stringent time constant. For instance, even 1 second delay could be very catastrophic. To put this in perspective, consider a case that car is traveling in 60 miles per hour, and in 1 second, it could travel in 88 feet, right? Which would be very dangerous if the ABS module is not activated, right? Within its timing requirements. Again, so just to give the consequences of missing timing constraint of those safety critical real-time systems. let me give another example. I think it will play. So in this case, see. So in this case, we are showing one example of airbag deployment in a car. So in the left side of the screen, it shows the normal deployment, what it's supposed to be in practice, and the right side of the screen shows if for some reason the airbag deployment process is delayed for whatever reason, right? So let me play it. As you can see here, in the play. Anyway, it's not playing here for some reason, but if the just to show what the videos should be, so if the airbag deployment process is delayed for a while, it could cause serious safety concerns for the passengers. So in the right case, for late deployment, if we can play it, it knocks the head back of the passenger pretty badly. So in other words, what I'm trying to show here, for time critical real-time applications, missing the timing constraint could be very catastrophic and could lead to very serious safety concerns for the humans, operators, and others around it, or even environment. Now, speaking of the other properties of real-time applications, so because those are embedded applications, we have a very limited availability on the in terms of available computing power, memory, and also some of the real-time applications are battery operated. So we also have constant on energy. And another distinguishing feature of real-time cyberphysical applications is that they are modeled by periodic applications. So in real-time task applications, they invoke periodically within certain interval time, and they must finish their computation within the certain time constant that we call deadline, as I said. And also they use priority-driven scheduling, which means the system has some predefined priorities of the application. And when a high priority application arrives in the system, again, this is a periodic application, periodic system. So it will print the currently running process, and then high priority process will be sunk. Okay, another properties of real-time applications, which will be the focus of remaining part of my talk, that the real-time cyber-physical applications are based on sensing and actuation. Because this is the cyber-physical application, it sense the environment, and based on that, it provides some application command to the actuator so that the cyber-physical system remains operational the system remains operational, right? Again, consider one example of cyber-physical application like the drone, right? The drone sensor takes different measurements like the altitude and other GPS signals and send corresponding command to the actuator so that the drone remains stable during its mission, right? Now, what we are trying to explore in this work is that how can we ensure the integrity of the sensing and actuation process? Because if we send any false or spoof command in the actuators, it may cause serious safety concerns for the underlying application. To give you some example, again, consider a drone. We're considering a quadcopter. So say we have 4 propellers in the drone. Now, because of the nature of these applications, the drone propellers need to move in a certain direction to make it stable during flight. For instance, if one side of the diagonal rotors move in clockwise direction, the other needs to be moving counterclockwise so that the drones, all the propellers remain stable in the azimuth, right? Now consider a case when if the attacker, some bad guy, who wants to disrupt the normal operation of the system and just flip the rotational direction of one of the propellers, right? One of the motor's signals. Then this could disrupt the whole operation of the drone, and it may not be stable during flight. And in this case, as we can see, for attacker's point of view, we don't need to compromise all the sensors or actuators. Just flipping one of the motors could be sufficient to make the system destable, right? And because of the safety critical nature of the system, safety considerations, both timing and safety constraints are very critical to ensure that the system remains operational during its mission. So the question we are exploring in this work that I'll be discussing today, that how can we prevent falsification of actuation commands and ensure the actuation command sends to the physical actuators remain trustworthy. So let's go ahead, but before I start talking about the key ideas, any questions so far? No? Well, good. Okay, so let's jump into the details. Again, I keep it a very high level, and please feel free to stop me if you have any questions on point. So what we are doing here, so we want to examine the actuation commands before they are the actual commands, the digital command sent to the physical actuators, and the actuators can act upon this the signal it's getting from the applications. And again, because we are designing for real-time cyber physical applications, we need to ensure the timing constraint must be met, because when we do some additional checks, it will cause some extra delay, right? So we need to take care of those extra overhead and ensure the timing constraint for the end-to-end system remains satisfied. And also we need to ensure that the solution we design is temper resistant, right? If the solution, whatever checking mechanism we develop can be compromised by the attacker, there's no point, right? So we have to design a tamper-proof solution. And also we have to provide better compatibility of the existing system so that we don't need extra hardware or software component in the system. So we want to design a solution that can be used by existing off-the-shelf systems. So we achieve these last two properties, temper resistance and compatibility with off-the-shelf system, using emerging technology called trusted execution environment, or TEEs. Specifically, we use the Trustzone feature available in modern ARM processors. So I'll talk about TEEs and Trustzone in details when I go to that topic. But again, giving you just some idea that these systems will provide better compatibility with existing system, and the solutions we are designing is temper resistance from adversarial actions. So what is the applications we are considering there? Again, we consider real-time applications. So we have a set of real-time applications, and because this is a periodic, this is a real-time application, so the applications are arranged in a periodic manner. We consider a system with multi-core chips. So the underlying system on chip may have multiple processors, and the applications running on the processors are scheduled in a way that we know which applications is running on which processor, and there has been known algorithms to do that. And because this is a multitask, so that by task I mean we consider is analogous to process in any operating system, right? So each task generates a bunch of actuation commands, and our goal here is to examine those commands. And for attackers' capability, we consider a case where attackers' action would compromise the normal behavior of the flat or cyber platform, and how the attacker could compromise the system. We don't have any explicit assumptions. It be used by any existing technique like social engineering, using some known vulnerabilities or remote trojans. So we don't have any explicit assumption on how it could be compromised, but we are more focused on after effect of the compromise. And also don't consider any physical presence. So don't consider a case where the attacker could have a physical presence to the drone and then physically change any actuators or sensors. So don't consider any physical damage, compromise. So let me talk a little bit about the whole operation, how this actuation process occurs in the system. Let's consider a simple controller task. Say, again, we are considering a UAV example. So we perform some computation to make the to get say sensor measurements or do some other kind of computation for instance, image processing and whatnot. And then after some time, say we want to send some actuation request to the actuators. So we want to send the propellers to move in certain direction or certain angular speed. Right? So what happened in a regular system, traditional system, when the actuation request is sent, say in this case, we are setting the motor direction of one of the propellers. So that direction already directly translate the motor propellers. And what is those commands? Those are some numbers, some decimal values sending to the motor propellers to inform it move in a certain direction. Now, there is no way to verify that is the values sent to the actual hardware, actual propellers in this case, is the one we expected for correct operation of the system. So for example, say the default operation for motor, propeller we expect is say clockwise. But there is no way to verify that what the application says, whether it is clockwise or anti-clockwise, whether the range is within a certain bound. So there is no way to check in the current image. So now, again, the question we're answering, how can we vet this? How can we verify this? What is the values is coming from the applications and what's the expected value required for correct system operations? How do we correlate this and ensure that the correct value is always transmitted by the applications, right? So what we do to address this question? So again, so consider the same application. So say we are considering a case where we want to send some direction value to the propellers. So in this case, we propose to use two execution mode for the operation of the drone or UAV. So what are those modes? So there are two modes. One is the normal execution mode, like before, what you see in the earlier slide. In addition to that, the system can operate also in a trusted execution mode. How we can achieve that? Remember the idea about trusted execution environment or trust-zone technology I mentioned. So we can use this, we can achieve this by using the trust-zone technology. So existing chips provides a way to operate in two different modes, where one mode could be used some high performance computing with all system functionalities, and other mode, which could be the secure mode, we can use for running very small tasks specifically for security purposes. So borrow the same idea from trust-zone technology and enable two execution mode for cyber physical applications, specifically for protecting the actuation commands. So what happened in this case, when a task, real-time task generates an actuation request, so that request will be transferred to a trusted execution mode, where we provide some kind of checking to ensure that this is the actual command that the hardware is expecting for correct system operations. In this case, for example, our desired angle of the desired direction of rotation is clockwise. We will check whether the same command sent from the application task is clockwise or not. If it's clockwise, then only it will be bypassed, it will be forwarded to the physical hardware. Otherwise, it will be denied. Now, how do we know which command is needed for correct operation? So we use a rule-based checking mechanism that maps the system state with the set of actions. For example, if we relate with the previous case, examples of the quadcopter. So in this case, the system state is the direction and which direction it will move, and the action is the corresponding rule. Like for instance, let me show. Yeah. For instance, if we want to control the say front left motor, then the direction should be clockwise. If we want to move the other motor, so for instance front right, the direction should be anti-clockwise. So here we map the current system state to corresponding actions. But so far so good. We have a two execution mode where we have a way to check each of the execution commands, right? And we also provide tamper-proof guarantees by using a trusted execution environment or trusted technology, right? So far, so good, right? So what's the catch here? What could go wrong? So the problem is, remember about the timing constraint we mentioned earlier, right? Because of this, the nature of real-time applications, we need to take care of additional overhead and ensure that no matter what extra overhead we bring, the checking should adhere to the real-time guarantees, right? So the problem with real-time system, with applying the techniques like this in real-time system. So applying technique like this in real-time system, that it will add some overhead and it may lead a system to an infeasible state. So what do I mean by that? So let me clarify a little bit on the timing constraint and what would be a problem in this case. Consider a case, we have just one task in the system. And remember, this is a periodic system. So each job or each instance of a task arrives periodically in the system. If we have just one task in the system, one application in the system, it arrives, it do its computation, and it completes, right? But recall that we consider a multitask priority-driven scheduler, right? So which means if a task arrives and at the same time, consider a case, a task arrives and some other task running in the system. And if the newly arrived task is with higher priority, it will preempt or it will stop the currently running task and then schedule the one with highest priority, right? So we need to account the delay due to the execution of other high priority tasks. So likewise, so when we perform the checking, we need to consider the additional delay due to the checking, plus the delay we experience from execution of other high priority tasks, and consider this total delay and ensure that this delay is less than our timing constraint or deadline, right? And if this is the case, then we can say that our system is feasible and it remains functional while we deploy it, right? Now the problem comes with this overhead part, because now we have a two execution mode system, and when we receive any execution command, we need to send this to the trusted mode for additional checking. And as we shall see, each of those checking and transferring the context from normal mode to secure mode is not insignificant. So there is a significant cost associated with that, and that could be a problem for real-time applications. So let me elaborate a little bit on that. So to understand this problem, we need to know the details about the trust-zone technology that we use as a backbone for this framework. So how trust-zone works? So it operates in, again, two modes. One is the normal or untrusted mode, where we can use any regular traditional operating system like Linux. So in trust-zone terminology, so this normal operation mode called normal world. In addition to that, trust-zone also provides a secure execution mode. It's called secure world in trust-zone terminology, that provides a very small, minimally verified kernel, and also it provides a user space layer where we can write small security critical applications. And these two modes, how can we provide context switch between these two modes? Trust-zone provides some APIs called secure monitor call that is responsible for transferring the data or context back and forth between these two worlds. Now, if we use this trust-zone technology to secure the actuation command or check the actuation commands, so we need to take care of this overhead of data transfer between normal and secure world, because we need to transfer the actuation command request from normal world to the secure world, and then in the secure world we could do some additional checking. So speaking of the data transfer, so this data, as I said, is transferred by running some performing bunch of API calls, or also known as secure monitor calls. And we do so by by calling a bunch of API calls. So let me show you. So it is doing in steps. So we need to do some initialization and then create a session between the trusted mode and the normal mode. And then we need to send the data from normal secure world. In this case, we are transferring the actuation command from one world to another world. And then finally, we clean up the session. Now, if you see, Trustzone developers provide specific APIs for each of those operations. But the problem is that, so these operations are costly, specifically for, if we consider for embedded and real-time cyber-physical applications. So in the slide, I put the numbers we observed from running each of those API calls on a Raspberry Pi embedded platform. And in total, just doing a API call for checking, opening a session for checking actuation command. For each of those calls, it takes roughly 66 millisecond overhead, so which is quite large. If we consider a task may have multiple of those actuation commands, because often the timing constraint of the systems, real-time system, could be much less than this overhead. So, for instance, if a drone or rover or any real-time cyber-physical application operates in 5 hertz, we need to ensure their end-to-end latency, so from arrival to finish, should be done within 200 milliseconds. Now, checking one actuation command, if it takes 66 milliseconds, it should be very high, considering the case that we have some additional delay, like actual task computation, then delay from execution of other high-priority tasks, and so on and so forth, right? So, what can we do? Can we do better? How can we address this problem, right? So to address this, we came up with the idea of selective checking. So because we cannot check all the commands because of this overhead, why can't we just check only a few to ensure that timing requirements are met, right? So let me elaborate. So what is this selective checking idea? So instead of checking all the commands, we will check only a subset of it to reduce the checking overhead. So for example, consider a case when a task generates a bunch of n actuation commands. So instead of checking all n commands, only we will check a subset of them and then check it, right? But the problem with this subset checking or selective checking approach is that how do we know which subset we will pick for checking, right? Because say we pick some subset of the commands for checking, but the adversary compromise some other commands not within the checking set, then there's no point, right? Again, we have the same problem. Your commands are not verified, right? So the now question is, can we do better, right? And the answer is yes, we can, and that's the focus of my next couple of minutes talk, that we present a new idea we call Selective Checking and Trusted Execution Framework, SCADE, that we published in last year ISOR. So what this SCADE idea is that instead of checking all the commands, we non-deterministically select a subset of it and use for checking. So what do I mean by that? So in this case, again, same idea, we will not check all, we will check only a subset. But from adversary's point of view, we want to select the set in a way that it seems we check all the commands. How we do so? For example, see, for one invocation of jobs, we check, say, command 2 and 3, and then next invocation, say, 1 and 2, and so on and so forth. But we did it in a way that from adversary's point of view, it seems we check all 3 commands in each of the invocation of the task. And how we do so? So, for instance, say we have 3 commands, and we want to look it like from attacker's point of view that, so, and for each invocation of the job, instead of checking 3 commands, we check 2. But from attacker's point of view, we want to look it like that, we check all 3. So how we do so? So from 3 commands, if you want to pick 2, So there are three ways, right? Either 1 and 2, 2 and 3, or 1 and 3, right? So we assign probabilities of each of these selection ideas. And say, let's say we assign some probabilities to each of these actions. And then we generate a fitness function to select which subset we will pick. For instance, if we assign probability for checking the first one is 0.5, we generate a random number and see if the random number is less than 0.5. If so, we check, say, A1 and A2, and so on and so forth. Now, if you see in the bullet, we mentioned that we assign some probabilities, right? Now, how can we derive those probabilities, right? So to do so, we use a new game theoretical analysis analytical model that creates a game that established a great game between two players. I'll talk about this just in a second. And end of the day, we solve a linear optimization problem to derive those probabilities. So let me elaborate a little bit on that. So we design a game-based model. Again, I'm not going through in details of game theory and underlying analytical model, but say we consider a game between two entities here. One is the designer, like us, and the attacker who wants to disrupt the system. And we define two parameters, system reward and system cost. So, for instance, from attacker's point of view, say we check some actuation commands, and the designer, the attacker compromise some other actuation commands. Say we check AI, and the designer, the attacker compromise AJ, another command. Now we define two functions: system reward and system cost. So high reward and low cost, which means good for the designer. So we check some command and which is not compromised by the attacker. So which means it's good for the designer, and the other way around is good for the attacker. And now, because we only check a subset, there are many possibilities of those combinations, right? That we can check and the attacker could compromise. So to find out this balance between this cost and reward, we formulate a linear optimization problem that maximize the reward and minimize the cost, which means this is good for the system designer's point of view. And based on that, it derives the optimal probabilities that minimize the chances of intrusion. So in other words, so the subset we select for each of these instance of the task will always provide better reward for the designer, and likelihood of missing, likelihood of compromising the non-checked command by the attacker will be very low if we select the probabilities with this formulation that we derive. So I'm not going to the details of this map, but let me show some results. So we tested this on Raspberry Pi platform, and if you want to check how our implementation may look like, so you can go over this link. So we tested on 4 different cyber physical applications, from rover and a drone prototype and a medical application, syringe pump, and also a robotic arm. For the interest of time, today I'll just talk one result from one platform, or rover platform. So in this case, the actuation commands are the setting the speed of the wheels of the rover and also the direction which way it will travel. And in this case, the checking were performed whether the command set to the motor encoders are within certain range or not. And in this case, the attacks we are considering denial of service attack, where the attacker sends some arbitrary high speed to the motor encoder to destabilize the rover. So we consider 3 cases. So we compare SCADE with another approach called fine grain checking, where we check all the commands, but again it comes with a cost because it will increase the delay. So what we find that because now, so here what we are doing here in the Y dimension, we are seeing the delay of checking the actuation intrusions, right? So because now we are say we are checking some commands, but the attacker compromised some other commands. Now, because we are doing selective checking, it may be the case that we detect the compromised command after certain instance later, right? Because we are not checking all the commands. So we are now measuring what is that additional delay that comes due to not checking all the commands. And what we found that because of the selective checking, there is some delay. We are not detect the intrusion instantaneously compared to the fine-grained one where we check all the commands. But that delay is not very significant. In the worst case, we take 3 additional invocation of a real-time task to detect the delay. And in the best case, on average case, it just takes 1 extra instance to detect the delay. And also, we study the overheads of running this scheme on Raspberry Pi platform. So in the X dimension, we show different scheme. One is the fine grain, where we check all the commands, and one is skate, the one we propose. And in addition to that, we also consider another case where we don't use any checking. So we run it natively, and the Y dimension shows the corresponding execution time. So as you can see, if you don't check any commands, then there is no keys or trust zone, so there is no API call overhead. So the delay is very insignificant. But for checking all the commands, it adds up the overheads of checking the commands and calling each of those trust zone APIs. So it creates a significant overhead. And as you can see, the red line here shows the task timing constant or deadline. And find the scheme, the middle one, exceed that, which means your system is not schedulable, it's not feasible, so it will not work if you deploy it. But in contrast, the one with selective checking able to complete within the timing constraints. So what we observe in this paper, so we are finding a way to provide a trade-off between real-time and security guarantees. Because how this trade-off comes, so for better security guarantees, it would be ideal if we can check all the commands in the system, right? And ideally that would be the best case, but we cannot do because of this additional timing constraint we have, right? So this skate idea provides a way to balance between real-time requirements and security requirements and find the best trade-off where instead of checking all the comments, we only check a few with the cost of adding some delay in the detecting the intrusion, right? But again, if that selective checking idea manages to ensure the timing constraint are made, right? And at the same time, also try to maximize the security. So having said that, so today what we will discuss is see one idea of protecting the actuators in time-critical cyber-physical application. And we do so in a way that we provide a security, but at the same time, we ensure the timing constant, right? So in this case, if you see, we put real-time guarantees on the front side, right, on the front foot, and then trade off on the security side. But also we could design a knob that tune the other way around, right? For instance, here we trade off security for ensuring timing guarantees. So we perform selective checking. We could do the other way around. So we check all the commands, and occasionally some tasks may miss their timing guarantee. But if we can bound somehow that, okay, probably after M out of K instance, we only miss 1 or 2 deadlines, right? And if we can find a way to tune the system so that still, despite having some delay on certain invocation, still the system remain functional, then this way we can maximize the security with the cost of some real-time performance leakage, right? Those could be some open area that we can explore. So having said that, let me conclude, and I'm happy to have any questions. Oh, questions? Questions, comments, or am I going too fast?
You mentioned the GitHub repo for this project. What exactly is on there?
So all the implementation we do. And if you have the actual platform, you can actually deploy. And if you want to deploy, we are happy to provide. Any other questions? Yes.
So I think there was like a slide about, you know, assigned random words, so. That, so. Would you wanna, is that based off like the probability?
This one,
Of like, probability.
this one, right?
Yeah.
Okay. Yes, so those probabilities. This is just an example. Showing you how can we say, for instance, here, we select, so we have say 3 commas, we only select 2. And based on this probability, say, each time you want to check, you generate a random number and check your random number is less than will be same. If so, then you check A1 and first 2 numbers. If your random number is generated within that range, you check 1, 2, and 3. For instance. This is based on you know this probability, right? But the question is, how do you know this in the first place? For that, we use the range. Yeah, and again, this is a very simplistic example for 3 commands, right? If you have many commands, then it will be very complex. That's why information will be.
How many commands do you see in a real drone or rover? Hundreds, thousands.
It's not like that. So 20, 25. For each unit, for a given task. Now we could have many tasks. Any other questions? Okay.
Thank you very much.
Thank you.